Hello everyone. So we are going on the next session, which is dealing about material processes and chain opératoire, the second part. I'm Niels Blanc from the Institut and the Beamline BM2, French CRG at the SRF. And I'm pleased to welcome Victor Gonzalez from the Rijksmuseum. And you have 40 minutes.
Thank you, Niels, for the introduction. I want to start by thanking warmly the organizers for inviting me. It is very nice to be here at the ESRF because I do remember that my first Beam time ever was here on ID 22, I think. So yeah, it feels really nice to be here with my community. And today we are back to structural studies that Koen Janssen already discussed yesterday, but I'm going to present to you some other cases which you might find interesting. So, today, I'm going to try to convince you that synchrotron radiation, and most specifically structural studies using synchrotron radiation, can bring us some answers to questions that we have when we are dealing with historical paintings, and most specifically inorganic pigments. And to do that, I'm going to showcase a few examples which will have to do with the materials and techniques of Leonardo da Vinci, the creative processes at stake in the work of Rembrandt, and finally, I'm going to briefly discuss the in situ formation of crystalline compounds in oil paintings. And at the end of my presentation, I will present to you a few open questions for us as a community to see, perhaps to reflect together on what the EBS will mean for us and what we will be able to achieve in the future. So, as a very brief introduction, but this was already presented this morning and yesterday, historical paintings are very complex objects. The reason for that is that the materials which compose them are quite unknown to us. So for example, if we are dealing with a pigment and we want to know how it was prepared in the past. So when we are dealing with this type of recipes, you can imagine very easily that it's difficult to understand. And when we do have some insights on how the pigments were prepared in the past, well, we quickly realize that those synthesis processes are very complex. So in the case of lead white, for example, Koen yesterday already discussed this pigment, and I'm going to talk a great deal about it today again. We know that lead white was obtained by placing metallic lead in the presence of acetic acid in jars, and those jars were covered up in horse manure for several months. And this induced the corrosion of the lead, and then the powder was collected, post-prepared with some post-synthesis processes, and finally we obtain the pigments. So we might think we know something about this pigment, but actually when we look chemically in detail what is going on at the various steps of this process, it's actually very complicated. For example, the corrosion process for lead white involves a lot of intermediate crystalline phases and so on. So elaborate ancient synthesis with unknown parameters. The second order of difficulty when we are dealing with inorganic pigments and historical paintings, and this was presented again this morning, is that those paintings are very dynamic objects. So Frederike this morning presented you this exact same example of these yellow roses, and to convince you that something happened here, well, this is the chemical imaging of arsenic, so you can see that this flower, which was so delicately painted in the past, now has lost a part of its beauty. So again, dynamic materials undergoing chemical changes at the microscale. So to try to overcome these difficulties, what we are used to do is to go to synchrotron facilities, and to do that, this was already told again, we are used to collect microsamples carefully at the surface of paintings and bring those samples at the synchrotron, where we will rely on the state-of-the-art analytical capacities in order to perform some very advanced characterization. And in my case, I will deal mostly with the structural study. So, what does it mean, structural study for me? I'm going to look specifically at several parameters which I find are of interest when trying to understand the materials I'm dealing with. So, in the case of lead white, for example, 3 specific parameters are very interesting to me. We know that lead white is composed of 2 lead carbonate phases, cerussite and hydrocerussite. Well, using synchrotron radiation, I will try to access a precise quantification of those 2 phases, perhaps access their distribution at the microscale, or they are placed next to another in a complex paint stratigraphy. And finally, I will try also to access the crystallite sizes, because this also is a clue on how the pigment was prepared and evolved. So let's start with some example regarding Leonardo da Vinci. So we are going to focus specifically on its use of the lead white pigment. So as I told you, we know that the lead white pigment in the times of Leonardo was prepared through this corrosion process. But actually what we are very interested in is those post-synthesis process. We know that it was very unusual for painters to use the raw material directly in their painting. We know that they were using several post-synthesis processes before accessing, let's say, a pure pigment or a pigment which was considered as beautiful to paint with. And what we think is that those post-synthesis processes actually have an effect on the structural nature of the paint. So this paint, which was post-processed, has a specific structural signature. Our research convinced us that actually when you obtain a raw lead white pigment, it is most of the time in a classic, what I would call the classic ratio of hydrocerussite-cerussite greater than 60:40. So usually a pigment which was obtained through the classic way of synthesis is richer in hydrocerussite. But what we know is that in Leonardo's time, several post-synthesis processes were used in order to make the pigment more, let's say, suitable to paint with. One of those post-synthesis process consisted in washing or grinding the pigment in acidic environment. While by reconstructing this post-synthesis in the lab, we were able to see that actually because those lead carbonate phases are balanced through a pH-dependent equilibrium, washing in vinegar will induce an increase of the cerussite, which is stable at lower pH. Also, the dissolution and recrystallization will induce a decrease of the size of crystallite. On the opposite, another historical processes that we know of consisted in washing the pigment in aqueous environment. And in this case, we have the opposite effect, meaning that the amount of hydrocerussite will go up and the size of crystallite will increase. So basically, in the case of Leonardo, we were lucky to find some indication that indeed he used different subtypes of lead white. We know from a manuscript that he paid a certain amount of money for one lead white and an amount which was greater for another lead white. So most definitely, he used different grades of lead white. The question for us will be, well, can we find those different qualities of lead white in his paintings? So, of course, it's not the workshop of Leonardo, but we can imagine that things went quite similarly in his workshop. The master is here working, but what we are interested in is the work of those two apprentices. They are preparing the pigment using specific recipes, and we want to try to decipher those recipes and perhaps finding them again within the artworks. So to do that, the first step when we were working on lead white pigments consisted in going to the ID22 beamline at the ESRF to perform high-angle resolution X-ray diffraction. So in this particular case, this is a powder diffraction beamline. So the trick was to place our microsamples in glass capillaries. This is kind of tricky, but it works. And then we are going to actually irradiate those samples at quite high energy because we are working in transmission. We are probing the entire bulk of the sample, so you have to be extra careful in having a sample which has only one layer of lead white because the contribution of all your lead white will be mixed. And then we are working in transmission, meaning that the detectors are somewhere around here. And using high-angular X-ray diffraction, we are able to have some very, very high-quality data sets of structural information. And again, I'm interested in the quantification of my phases and the size of crystallite. We did that for a lot of samples of lead white. And if we plot the ratio of hydrocerussite on cerussite versus the size of crystallite, we can see that some groups are appearing. So I won't get into too much detail, but basically we can think that, for example, some samples which are characterized by a low amount of cerussite and a small crystallite size might be connected to a post-synthesis treatment in acidic environment. So the game then will be to try to think where Leonardo's sample fit in those groups. The main idea is that structural analysis can provide some information on the preparation recipes of historical pigments. So I'm going to present, to showcase an example which is even more precise in the case of Leonardo. So when we were reading Leonardo's manuscript, we were very surprised to find a very nice story that Leonardo actually had the insight of Rayleigh diffusion or Rayleigh scattering in the past. Because indeed, he postulates that the blue color of the sky is not its intrinsic color, but is caused by sorry, is caused by small insensible atoms on which the solar ray falls, rendering them luminous, which is quite correct, actually. But Leonardo goes a step further, and to convince us of that, he says, if you want to be convinced, you can use ceruse, this is lead white, take it and a very fine and well-grinded ceruse, and it will have a beautiful blue. And this is actually true. If you take some lead white composed of nanometric crystallites, it will have a blue hue. This is particularly visible here. We reconstructed this in the lab. So we synthesized the lead white with nanometric crystallite, and you can see indeed that this white has a very beautiful blue hue. On the opposite, if you have a lead white with big particles, well, it's very covering. This is basically a very white pigment. So what was interesting is that all the ground layers of Leonardo da Vinci, so the layers which he used to prepare his painting before going to his composition, all of those ground layers were characterized by a high amount of cerussite and a very big size of crystallites. And we think that it's actually, let's say, something which was well thought of, because when you use this type of big particles, they will recline under the brush, and you will obtain a paint layer with an optimal covering power. All of those paint layers have big crystallites, are composed with an amount of hydrocerussite which is very high. We can perhaps propose that they were obtained through a post-synthesis treatments consisting in heating in aqueous environment. But when we go to this specific painting by Leonardo da Vinci, we had access to an exceptional sample which is located here in the mountains in a place which is very bluish white. So it's a place of the location of the painting where Leonardo was interested in having perhaps some kind of this blue white pigment. And indeed, it was very convincing that this top layer had just a few blue particles, but was composed of nanometric crystallites. What's more, we found that this lead white is indeed composed of something rich in cerussite. So this is kind of something that Kuhn presented yesterday. We have here a lead white paint which is rich in cerussite with nanometric crystallites. So we thought, oh, maybe this has to do with some kind of post-synthesis treatment in acidic environments. But we wanted to confirm that, go a step further. And to do that, we were interested in looking at very precisely the microstructure or the peak shape of our pigments. Indeed, something we noticed, and which is absolutely impossible to do if you don't have access to very high quality data sets, so very high angular resolution like at ID22, is that a lead white obtained through corrosion is, let's say, characterized by what I will call a good crystallinity. So when you obtain lead white through a slow corrosion, your diffraction peak, this is a zoom on 2 peaks of cerussite, will be nice and symmetric. But if you induce some fast crystallization, you will obtain what is called crystal twinning. So in this case, you have asymmetrical Lorentzian broadening, and you can see that your peak on the left here and on the right, they are starting to broaden. This is actually a natural crystal, and this is something that we obtained in the lab when we made sure to induce some fast recrystallization. Well, sure enough, what was very interesting to us is that the cerussite of Leonardo did show this broadening of peaks. And so to us, this might mean that indeed this is a clue that this specific lead white rich in cerussite with nanometric crystallites and with this broadening might be indeed obtained through this post-synthesis. So you can see here how synchrotron radiation can allow us to go a step further and try to have very precise clues on how the pigments were obtained in the past. Now, I'm going to showcase another example, and this is some work which was performed over the course of the last year, 2 years at the Rijksmuseum Science Department. We were interested in Rembrandt Impasto. So for those of you who don't know what impasto is, it's this very thick paint. If you've been in front of a Rembrandt painting, you can, if you go close enough, you will see that the paint actually stands out of the canvas. It's really a tri-dimensional aspect. We knew that Rembrandt Impasto was based on lead white, so this mixture again of hydrocerussite and cerussite, but the precise recipe was unknown. So our idea was again, let's take some cross-section from impasto area and non-impasto area and see if we have some specific structural features. So again, back to ID22, well, the first thing that we observed is that in all of the impasto samples that we had, a mysterious phase was showing up. Plomonacrite, this is another type of lead carbonate, but much less common than hydrocerussite and cerussite. It was detected before by Kuhn Jansson's team in Van Gogh painting, but it was linked to the degradation of orange pigments. So in our case, it was very interesting to see that all impasto layers seems to be characterized by this presence and in high amount of this plomonacrite, which was linked to impasto. As usual, we also wanted to have information on the microstructure of this phase. And what was interesting is that within the classic lead-white matrix, well, our crystallites of plomonacrite were of nanometric sizes. So we had this nanocrystallites of plomonacrite within a lead-white matrix of greater size. Okay, so the idea after that was, let's see if synchrotron can help us see where those specific phases organize themselves within the paint stratigraphy. So to do that, we switched to another mode of synchrotron analysis. This is structural mapping, and it was presented to you several times already. So the idea is simple. You have your microsample, and you will translate it in front of the beam in order to map a larger area. So what you will do is translate your sample. The sample is actually moving. And in the end, what you obtain is a map of the distribution of your phases. We did that at the ID 13 beamline at the ESRF. So you can see here, the sample is here, the beam comes like that, and we have our translation. This is a detector. In this case, we were working at 13 kiloelectron volt. So we need to work on thin section because the amount of matter that we will go through has to be minimal in order not to have too much shadowing. So this is something that Marine is renowned for, is the preparation of thin section. The idea is that we will cut a piece, a very thin piece of the cross section in order to have a very limited amount of matter so the X-rays can go through. Okay, so what we were lucky to have is a very nice sample from the Louvre where we had one layer of impasto, this white layer, directly on top of a white layer, but which is not impasto. And what was, again, very convincing is that this plomonacrite phase was localized only in this impasto layer. The classic lead-white layer, which was used for the ground, was composed of hydrocerussite and cerussite, as you would expect. So it did seem, indeed, that plomonacrite is linked to impasto. And in other samples, so this is just a chip of pure impasto, I would say, we can see that this, in red here, the plomonacrite, is homogeneously distributed within the entire bulk of the impasto. So this is not something which is, for example, a surfacic phenomenon, like Laetitia showed this morning, where you can see this phase only present at the surface, which we might think then, it's a degradation process coming from the atmosphere. It seems that plomonacrite has appeared in the entire bulk of the sample. Okay, so we had a lot of clues, basically, this homogeneous distribution of plomonacrite in the form of nanometric crystal. So we thought, well, maybe this is connected to the in situ formation within the impasto layer. And now the question that we had, well, can we retrieve the chemical pathways of this formation? The main clue that we had is that plomonacrite is a metastable phase only existing at a pH greater than 10. So it's only stable in alkaline conditions. So from this, we were able to say, well, perhaps an hypothesis would be that Rembrandt used some litharge-based oil. We know that this type of oil was mentioned in historical sources, so it was not, let's say it's entirely possible that Rembrandt did use this type of oil. We know that a litharge-based oil has interesting drying and rheological properties, which might be interesting to build this very thick paint. So our hypothesis was, well, perhaps a mixture of lead white in the presence of litharge might induce the formation of plomonacrite. So to, let's say, confirm this hypothesis, we went back to the lab, prepared a lot of model. The internship of Tiffany Tang was done at the Rijksmuseum Science Department. And indeed, going back to synchrotron mapping, we were able to see that at the microscale, this is an undissolved litharge particle in an oil matrix. You can see indeed this nice ring of plomonacrite starting to crystallize around the litharge. So this is just a first step, but we think that the origin of plomonacrite can indeed be linked to the presence of lead oxide within the oil. Just, it could interest you, you have until the 16th February to visit this very nice exhibition in Amsterdam, where this work was showcased, and actually you can see here, the ESRF is present. So if you are in Amsterdam, you can see this nice exhibition where this work was showcased and a lot of other complementary works done at the Rijksmuseum Science Department. Okay, so very briefly, before my conclusion, I'm going to present just a few results regarding the in situ formation of mineral compounds in oil paintings, because this is something we are very interested in at the Rijksmuseum. As I told you, paintings are dynamic systems, and in this case, we are not really interested anymore in how they prepared the materials, but rather how the materials evolve over time. So they don't have control anymore on that, but today, in 2020, we can have an insight on how those materials have changed. So, for example, this is some work which was done with Catherine Koine on the presence of lead sulfate in historical paintings. Kuhn also showed some results regarding the specific crystalline materials. Well, in this type of paintings where we observe some very strong degradation, we were able, through structural mapping, to map the presence of those lead sulfate, either palmerite close to the surface or anglesite close at the interface between a ground layer of gypsum and a top layer. So for us, actually, what is very interesting and what is mandatory to understand is the origin of the ions which are necessary to form those non-original products. And in this case, for example, well, the lead is quite easily connected to the presence of lead white in the stratigraphy. But for example, the sulfur ion, we have several hypotheses that could come from the atmospheric SO2, so let's say pollution from the atmosphere, but also from the presence of gypsum. And what is interesting to us as well is that structural mapping at the synchrotron can allow us to see that those type of compounds don't always crystallize under the same, with the same aspect. So you can see here that in this painting, we obtain some thin layers of non-original materials. But on other paintings, they actually have a very different shapes. So we can see here in this painting where we had those protrusions, those big lumps of non-original materials protruding to the surface. You can see that palmerite here is not a thin layer, but it's actually this very big, let's say, lump within the lead-white matrix. And in this particular case, we think that this aspect, this way of crystallizing, can be connected to perhaps conservation treatments. So the main idea is that the distribution of those in situ formed compounds is critical to understand their origin. And actually, as Kuhn mentioned yesterday, we are right now involved in a very big conservation and research project on Rembrandt Night Watch. We are doing that in front of the public. And the presence of those non-original compounds is something we are very, very interested in the Night Watch. And I'm sure that when the ESRF EBS will start again, we will have plenty of interesting samples to bring at some point. Now, still on the in situ, I'm going to very, very briefly give you, this was already discussed through a poster clip, but this is a new project which involves several institutions, and it has to do with the presence of lead phosphate compound. So with Marine, as we were looking at the samples from Da Vinci again, we were surprised to detect this very thin layer containing phosphate. And actually, synchrotron microXRD confirmed that this layer was composed of phosphoediphane. What was interesting is that at the same time, Marine was working on Egyptian papyri, and in this papyri again, she detected the same phase. There is a poster, number 14, where you can read more about this study. And so basically we have questions because those lead phosphate, we don't know if they are original product, if they are degradation based. And what's very surprising is to find them at such a different, let's say, historical time and geographical. So the main question is explained in this poster, and all of these institutions are now collaborating on this new project on lead phosphate phases. Okay, so through this presentation, I hope I convinced you that synchrotron structural analysis can reveal the old masters' lost recipes, but also shine light on the evolution of their materials. So the question for us now as a community is, what about the future here at the ESRF EBS? So I'm going to present to you a few questions that we can maybe all reflect on together and try to think if we can maybe have some new directions to go as a community, not limited to paint studies, but when we can have access to this new instrument. So as a first example, something which will definitely change are the acquisition time. So I remember when we first came to ID22 in October 2014, we had to switch the sample every 2 hours. Now at ID22, you have robotic switch of pre-prepared sample, which means that you can go to sleep. It's very nice. You can prepare all your samples, and then they will be all analyzed as follows. But, for example, in the case of crystalline mapping, this is something that changed as well. When we were with Marine in May, so only 2 years ago, this was one night of analysis, and this was already particularly fast at the time, meaning that in one night we could map 15 samples or so. With the ESRF EBS, technically, we would reach such speed that in one night we could theoretically achieve more than 300 samples analyzed, which is ridiculous, because basically this is more than any usual corpus analyzed during a beam time. And the question that we should ask ourselves is, should we rethink our access modalities? Should we develop faster processing routes? Because this is something which obviously we'll have to change as well. And I'm pointing to this session on Friday afternoon, where the session Beyond Instruments and Data Collection, where I think we should discuss this type of questions. Something else is the question of new chemical probes. So in the past, we've been working with photoluminescence. This is something which was already showcased here during this workshop. And we showed that by exciting your lead white in the deep UV, you were able to perform some fast crystalline phase identification. Now, this was done in the lab. We know that at the ESRF, there is some, let's say, other chemical probes that we might be able to observe, to use. So, for example, Xiol, so optical luminescence excited by X-ray, is available. So the question that we should ask ourselves is, should we explore new probing techniques with this new ESRF EBS? But of course, then perhaps a theoretical approach is needed, because photoluminescence mechanisms are very complex. So the question maybe is, if we want to explore those new routes, do we want to go this direction? Okay, and finally, what I found the most interesting part for me is that the question is, can we get the best of two worlds? So basically, I'm used to work with high angular resolution on ID22, where you have obviously this state-of-the-art synchrotron data, but you have no mapping capacities, meaning that I map an entire sample. On the opposite, for example, on ID13, we have those excellent mapping capacities, and soon they will be extremely fast, but the angular resolution is quite low. So what you can do is perform some identification and charting of your different crystalline compounds, but that's about it. So let's say, as a dream, what would be amazing is that I can combine this mapping of my sample, but I can, let's say, selectively say, well, in this paint layer, can I have access on the microstructure of my sample? On this paint layer, can I modelize these particles of pigment? And there is this talk by Catherine, which is Beamline's post-ESRF upgrade phase, where perhaps we should discuss this idea of combining the high angular domain with the high lateral domain. So that's about it. I want to thank all of those people. I'm not going to list them all, but this work is obviously very collaborative and a lot of people are involved. And I want to finish by perhaps advertising for two meetings I'm co-organizing. The first will be held at the Rijksmuseum Science Department, and it's a workshop on the chemistry of lead in oil painting. So perhaps you realize now that lead is basically kind of omnipresent in oil paints, and this will be discussed here with a lot of excellent speakers, such as Kuhn Janssen, Reinkot, Laetitia Monico, always the same. And we have seven spots remaining, so hurry up. And the other meeting I'm co-organizing is the Gordon Research Seminar on Cultural Heritage Research. This will take place in Switzerland in July during 2 days. And this meeting is only dedicated to young research scientists. So young research scientists are PhD, postdocs. Basically, if you have a permanent contract, you're too old and we don't want you. But that's okay, because you can then join the Gordon Research Conference, which is organized by Loïc, who is here today, and which will be directly after the workshop. And here, all people can still submit abstract, Loïc told me. So you can also discuss with Loïc if you have any questions, and with me about those conferences. Thank you for your attention.
So the association of the Plumbo nechrite to the Impasto paint. So as you explained, this is through this oil, or could be through this oil.
Could be.
So I wonder whether the oil was then also used for non-impasto paint.
Sorry, you mean is there?
Yeah, is the connection exclusive to the impasto paint, or could the litage-rich oil also have been used by much more refinedly operating painters? That's what I'm wondering about.
That's absolutely indeed. This is a working hypothesis, but indeed, for example, in the case of impasto, there is now a new project being developed at the Rijksmuseum where it will be more focused on, for example, the morphologies of crystallites, and if this has something to do with the rheology. So there are different routes of to approach this painting, this problem. Sorry, basically the fact that plumbonacrite is present means that something is alkaline. So to us, this was the most obvious answer, this litarge-based oil. But it's, and I should say also that we have performed some other beam time, for example, at Diamond and I-18, where we have worked on a lot of model samples where it seems to fit with plumbonacrite crystallizes when litarge is present. But then, of course, is it only something due to the oil? It's, yeah, we still have a lot of work to do on this specific phase, and I know that your team detected plumbonacrite in obviously non-impasto layers because they are coming from other paintings, other painters. So this is perhaps not the only chemical pathway to plumbonacrite.
Some other questions?
Or it may be that in the samples where you detected plumbonacrite, it also comes from lead oxide.
Yeah.
But basically, our hypothesis is that when we found plumbonacrite, it means that lead oxide was probably used, and probably at such an extent or with particles so big that it remained available for reaction with CO2 and water to form plumbonacrite, even if there are probably many cases where litarge was used but completely reacted with oil to form lead soaps. So it may be a trace of remaining not for so long, because plumbonacrite forms in 1 month.
Fast,
yeah, very fast after the preparation of oil.
Yeah, a few hours.
One might ask the question of how the litharge was produced and whether it was a uniform phase. In Chinese art of the Song and Ming periods, we see litharge in coarse grains which has the consistency of a shell of lead oxide around a core of lead carbonate, and it affects the appearance. It gives it a brighter color. Depending on the way that the litharge was produced, in that case probably by roasting incompletely.
Yeah.
One might wonder whether the litharge used was really pure litharge.
Absolutely. So obviously the experiments we did in the lab was with pure litharge, but we do think that a key parameter is if the litharge is entirely dissolved in the oil or not. So according to us, well, so far it seems that the experiments are showing that you need to have some, let's say, still a remaining grain of litharge for this crystallization to kick in and start from this litharge. So indeed, perhaps the preparation method of the litharge could be connected to the dissolving capacities of the litharge in the oil and could be indeed linked to this specific chemical pathway. So this is indeed something very interesting to follow on.
And also related to that, lead oxide can be present as litharge and massico.
Yes.
And for example, in some text of Leonardo da Vinci, he mentions massico. So both may have been used and probably used as a mixture. Quite probably.
Yes, most probably.
If I may, just if you can come back to the slide where you explain the preparation of thin sections, since this is my favorite subject, just to make it clear, because the explanation which is given is in a particular case where the cross sections had been prepared maybe decades ago, and they were coming from a collection of cross sections. So it just to explain this particular case where we wanted to prepare thin sections, but years after the preparation of the original cross sections. So the cross sections that you see on the left was from a database collection of samples, and we wanted to extract thin section from this. And instead of cutting parallel to the surface of the sample. What you see here is that we decided to cut perpendicular to one side of the section. So meaning that even if you have samples which have been sampled, taken decades ago, embedded decades ago, and you consider that thin sections may be better than cross sections, is something we can do a posteriori, just to explain it. What I like in making thin sections is that you have a very good control of the volume which is analyzed. And in particular, when you do mapping in transmission with micro X-ray diffraction, you know exactly the volume which is probed, and you have a good chance that the composition is homogeneous in the beam direction. So this is my advice.
So if there's no more questions, we can thank you again, Victor.